my last lecture, I spoke about some of the postulates of quantum mechanics, and today I will continue to talk about the postulates. In particular, I will concentrate on the postulate relating to expectation values, basically the outcomes of experiments. So, postulates of quantum mechanics. And we were on the third postulate last time. So, postulate 3. Where I had introduced the concept of the expectation value of an operator. This is the notation. This operator stands for a physical observable pertaining to the system of our choice, and it is a very state dependent quantity and is to be understood in this manner. So, we have a basis set which is the eigenstate, the set of eigenstates corresponding to A with eigenvalues A1, little a1, a2, a3 and so on, and I itself takes values 1, 2, 3 to n. This is an orthonormal basis. And these are real numbers because A is a physical observable and therefore represented by a Hermitian operator. N is the dimension of the linear vector space, and that is why n basis vectors, which we have chosen to be an orthonormal basis set. To begin with, if they were not orthogonal to each other, we would use the Gram-Schmidt procedure and make it an orthonormal set. So, given this, you consider any state psi which is expanded in terms of this basis set in the following manner. And let us imagine that psi is normalized to 1. In that case, it is clear that summation over k mod c k squared is equal to 1. In general, psi may not be normalized to unity. In any case, given this psi, we showed that psi a psi was summation over k mod c k squared a k, and suppose you also had this denominator which was not equal to unity. This was simply summation over L mod C L squared, always going from 1 to n. Of course, I stopped at a point where I said that if this were normalized to unity, it simply means that the denominator is 1 and we need to give an interpretation here. It is obvious that the outcome of the experiment, which is the expectation value of A, is a weighted average, because it looks like A1 is going to be the outcome. The corresponding state, of course, would be phi 1 with a probability mod C1 squared. There is a weighting coefficient mod C1 squared. Similarly, A2 comes with a weightage mod C2 squared and so on. And this is what gives a probabilistic interpretation to quantum mechanics and measurement itself. Because I would do the following thing, I would say that A1 appears with probability mod C1 squared as the measurement outcome, A2 with probability mod C2 squared and so on. So, let us demonstrate this with a concrete example. Back to the 2-level atom. So, the Hermitian operator in consideration, let us say, is Sz. Given the states G and E, we had Sz when it operates on E gives me h cross by 2 E ket E, and Sz acting on G gives me minus h cross by 2 ket G. So these are the basis states, and I have chosen them to be eigenstates of Sz. It is clear therefore that if I have to find the average value of Sz, say in the state E, it is simply going to be h cross by 2 because it is already an eigenstate. Similarly, if I have to find this average value is minus h cross by 2. The expectation value is simply the eigenvalue in this case. On the other hand, let me consider a state psi is root 3 by 4 ket g plus root 1 by 4 ket e. Of course, it is normalized to 1 because this inner product is 1, this inner product is also 1, and the state ket E is orthogonal to the state ket G. Bra psi correspondingly is root 3 by 4 bra G plus root 1 by 4 bra E. And now I wish to find the expectation value of Sz, say, in the state psi. Have not put in the denominator because that inner product is 1, and I wish to compute this object. So I would do the following. First of all, I would find out the action of Sz on the state psi. Well, that is the same as Sz acting on root 3 by 4 ket G plus root 1 by 4 ket E. That is root 3 by 4 minus h cross by 2 ket G plus root 1 by 4 h cross by 2 ket E. Now I need to find out this object. Just to remind you, an operator acting on the state gives me another state in that linear vector space. So this is simply going to be root 3 by 4 bra G plus root 1 by 4 bra E with root 3 by 4 minus h cross by 2 ket G plus root 1 by 4 h cross by 2 ket E. It is pretty clear that this is 3/4 minus h cross by 2 times minus h cross by 2 plus 1/4 times h cross by 2. This is the probability with which the measurement outcome is minus h cross by 2, and this is the probability with which the measurement outcome is plus h cross by 2. In other words, I have several trials conducted because I need to look at the average value, the expectation value of Sz in the prepared state psi, ket psi, and it looks like 75% of the time my answer would be minus h cross by 2. The corresponding state, of course, would be ket G after measurement, and 25% of the trials would give an answer plus h cross by 2 with the state collapsing to the excited state of the atom, that is ket E. So this is expectation value of Sz. Of course, I can simplify it and write it for you as minus 3h cross by 8 plus h cross by 8. And that is equal to minus h cross by 4. It is clear that if psi is an admixture of states with the following coefficient 1 by root 2 in both cases, 50% of the time the expectation value would give me h cross by 2 as the answer, and 50% of the time I would get minus h cross by 2 as the answer. Let us recall that the measurement is made on an ensemble. On each member of the ensemble, the measurement is made once. After the measurement, the state collapses to either ket E or ket G in this case. Get to the next copy in the ensemble and make a single measurement, and so on. Take the arithmetic mean of the values, and that is the expectation value. One can ask the following question: we are expanding the state ket psi in terms of the basis states which are eigenstates of Sz. What is the expectation value of Sx, for instance, in this case? So let us take a simple example. Suppose I wanted to find the expectation value of the operator Sx in the state E. Now this is simply done because Sx, you will recall, is S plus S minus by 2, and therefore this quantity is simply half E S plus E plus E S minus E. So computing the expectation value of Sx reduces to finding out these expectation values, but S plus acting on ket E simply gives me 0, and S minus acting on ket E takes it to ket G, and E and G are orthogonal to each other, and therefore the expectation value E Sx E is equal to 0. Similarly, in the basis state ket G, we can show that the expectation value of Sx is equal to 0. Now let us look at the superposition that I considered earlier, and in a similar manner we can find out what the expectation value of Sx is in the superposed state. So once more I write psi as root 3 by 4 ket E ket G plus root 1 by 4 ket E, and I wish to find the expectation value of Sx in this state. So that amounts to finding out this object So S plus acting on psi to begin with, when S plus acts on ket G, it gives me ket E with coefficient 1 H cross, and when S plus acts on ket E, it simply destroys the state. Therefore psi S plus psi is root 3 by 4 1 H cross times the root 3 by 4 from this part times the root 1 by 4 because this part of psi would contribute to the expectation value. Recall that bra psi is root 3 by 4 bra G plus root 1 by 4 bra E. So what contributes would really be this combination, which gives me root 3 by 4 root 1 by 4 times 1 H cross, and therefore I simply have psi S plus psi. I need to take a half out here. Half psi S plus psi is half root of 3 by 4 1 H cross. I want to write this separately to show what the measurement value is going to be, what the outcome is going to be. Now we look at the other part, which is half psi S minus psi. Now S minus acting on psi, S minus annihilates G, it acts on E and brings it down to G with a coefficient 1 H cross. So psi S minus psi, this is bra psi, and therefore I am going to have a root 3 by 4 root 1 by 4 1 H cross. Of course, if I want to do half of this, that simply tells me that I have an answer which is half of that object. I believe here psi s plus psi has a root 3 by 4 times a root 1 by 4, so I should put that down. So that is what I have. I have psi s plus psi and psi s minus psi with a factor of half. The two of them can be added together to give me the expectation value of Sx in the state psi. I get the value 1 h cross with a probability this object, and I get the value 1 h cross again from ket G with a probability this value. So I can add them both up, and I just write this as whatever I have got from S plus minus S minus psi. So this is the way the expectation value of Sx is found in a state which is not an eigenstate of Sx or Sz, but which is expanded as a superposition of eigenkets of Sz. So much for expectation values of operators. The next postulate is about how exactly you go from classical physics to quantum physics, and the postulate says the following. So this is postulate 4. It says all dynamical variables in classical physics, let us say in classical mechanics, example position, momentum, angular momentum and so on, are replaced by operators, and in normal standard notation an operator comes with a cap like that in quantum physics. I have not used this cap in all my lectures till now to denote operators. One starts off by writing operators with a hat there, and then when one is pretty clear about what is the operator and what is the eigenvalue and what is the state, you could think in terms of dropping these hats and simply replacing x operator by x without the hat and realizing that it is an operator. Having said that, care must be exercised in the manner in which we replace dynamical variables by operators. For instance, you consider the x component of the orbital angular momentum. In classical mechanics, this is simply ypz minus zpy, where pz and py are components of the linear momentum p, and I have written this in Cartesian coordinates. So Lx squared would be ypz minus zpy times ypz minus zpy. And what would that be? These are numbers in classical mechanics. And therefore, Lx squared we can expand this as y squared pz squared minus zpy ypz minus ypz zpy plus z squared py squared. We need not worry about the order in which these things are written. For instance, this could well be written as ypy, and this could well be written as ZPZ. But in quantum physics, these are operators, and as you are aware by now, operators are represented by matrices which in general do not commute with each other, and therefore one has to exercise care in the manner in which this is written. I cannot, for instance, write this as y squared pz squared plus minus zy py pz minus yz pz py plus z squared py squared. This is one way of writing it, this expression, and this is the second way of writing it. They are equivalent as far as classical mechanics is concerned. But here I should be careful because I have interchanged the order, and in general p sub y and y, where p sub y is the canonical momentum corresponding to y, they do not commute in general with each other. And therefore, one has to retain the order as such. So, the manner in which this is to be expanded is ypz minus zpy ypz minus ypz zpy plus zpy zpy. So, that is the manner in which one retains the order of operators without changing them. Of course, when it comes to operators like spin, there are no classical analogues to worry about, and again the operators should be ordered based on the commutation relations between the operators. We could be thinking in terms of an operator like this. Say this operator. In classical physics, I can have an object xpx. In classical physics, that is the same as pxx. But if I go to quantum mechanics, should I write operator x, operator px, or operator px, operator x? How do I replace xpx? I should be careful, and the replacement would be like this. So, you take this combination, divide it by 2, and treat that as the operator corresponding to the classical object x px. This is a very important point, and care must be exercised because we are now dealing with matrices or non-commuting operators in general. Finally, there is a postulate which I will call postulate 5, which really tells us something very important. It tells us how to go from the Poisson bracket in classical mechanics to the commutator bracket in quantum mechanics, and that is how you go from one to the other. So, there is postulate 5. Consider a pair of canonically conjugate variables say x px. In classical mechanics, you have a Poisson bracket structure. By this I mean the Poisson bracket of x with px, that is 1. Of course, x with py is equal to 0, y with py Poisson bracket is equal to 1, and so on. The replacement is as follows. In quantum mechanics, the Poisson bracket is replaced by the commutator bracket divided by IH cross. In general, that is how one goes from classical physics to quantum physics. And the Poisson bracket between pairs of canonically conjugate variables is replaced by the commutator bracket, which is equal to IH cross. So, x px commutator is IH cross. I go from this commutator to the Poisson bracket through this operation, the commutator divided by IH cross. So when I go to classical physics from here, I get x px is equal to 1. So basically x px is equal to 1 gets replaced by x px commutator is IH cross in quantum mechanics, and this is classical mechanics. Now this is a very important statement. First of all, one understands that x is an operator, so if you wish we could put a hat here and a hat there. The commutator of two operators cannot be a number, so basically we mean that there is an identity operator there. If you give matrix representations, that is an identity matrix, which means you put 1 on the diagonal and 0 everywhere else. And x and px are also matrices, and they do not commute in general. The same goes for y with py, z with pz, angle and angular momentum, and so on. So pairs of canonically conjugate variables which have this Poisson bracket structure would simply go to the commutator equal to IH cross times the identity. Now some very interesting things can be seen right away. If these matrices were finite dimensional matrices, suppose I took the trace on both sides, these are operators. If these are finite dimensional matrices, we know that this is the same as saying trace of x px minus trace of pxx is equal to IH cross trace of the identity. And since trace is invariant under cyclic permutation, for finite dimensional matrices, the left hand side is 0, but the right hand side is definitely non-zero, because the trace is the sum of the diagonal elements, and the diagonal elements are 1 each. So when you add up, that is non-zero. It is pretty clear therefore right here that the only way out of this problem is to realize that x, px and so on are infinite dimensional matrices, and in infinite dimensions the trace, invariance of the trace under cyclic permutations does not hold good. In general does not hold good. So here is a very simple way of realizing that x, px, etc. are infinite dimensional matrices. That is, if I give matrix representation to these operators, they would be infinite dimensional. Further, I can find out commutators of x with px squared and so on. And if I did that, I see some interesting things. Given that x px commutator is IH cross, I am not writing the identity there, but it is there. What is the commutator of x with px squared? It is good in general to realize the ABC rule for commutators. Suppose I have the product AB, AB being matrices, the commutator with C. This is the same as ABC minus CAB. Consider this object. The commutator of B with C pre-multiplied with A plus commutator of A with C post-multiplied with B. Consider this. Now this is simply A times BC minus CB plus AC minus CA times B. This term minus ACB cancels with plus ACB, and I am left with ABC minus CAB. I have explicitly demonstrated by doing this that if I have to find the commutator of AB with C, that is the same as this object, all these being operators. Normally called the ABC rule and very useful for most calculations. In particular, I am going to use it here. So now x with px squared by this rule is x with px times px plus this object. Well, I could have done the same thing, and you could have checked that A, B, C, which is what I am using here, is AB with C plus B AC. All of them come with hats, they are all operators. So that is what I have done here. B is Px and C is also Px. This simplifies by that postulate 5 to IH cross Px plus IH cross being a number, I can pull that out, and that multiplies Px, which is 2IH cross Px. Now what is the commutator of x with Px cubed? Well, I can always write it as the commutator of x with Px squared Px. I use the ABC rule that say this is B and that is C, and therefore I am going to have x Px squared with Px plus Px squared x Px, which is 2IH cross Px times Px plus IH cross Px squared, which is 3IH cross Px squared, and so on. So by induction, it is clear that the following relation holds. The commutator of x with Px to the power of n, where n is some positive integer, is NIH cross Px to the n minus 1. This is one of the things that I have come across now. I am going to see another result soon. Suppose I found out Px with x to the power of n, where n is a positive integer. I would do the same thing. I would say that Px with x is minus IH cross. It is easy to check that the commutator of A with B is minus the commutator of B with A. Of course, there is an identity here. Px with x squared by the ABC rule is this object. That gives me a minus 2IH cross x, and so on. And finally, I could have Px with x to the power of n is minus NIH cross x to the power of n minus 1. Now suppose I consider an operator which is a function of x and p. Consider an operator A which, let us say, is x to the power of n, Px to the power of m. And suppose I wish to find the commutator of x with A. Well, by the ABC rule, I could call this B, that C, and this A. This is the same as the commutator of x with x to the power of n, Px to the power of m, plus x to the power of n commutator of x with px to the power of m. This is 0 because x commutes with itself. So the first term drops out and I just have x to the power of n, and I already have this result. I put that in there and I just have m I h cross px to the power of m minus 1, which can well be written as I h cross x to the power of n m px to the power of m minus 1, which is the same as I h cross d by dpx of a, because a had px to the m and that brought down the m and gave me a px to the power of m minus 1. You will notice that I have removed the hat from the operator p, but that is because I am now thinking in terms of the momentum space, where the operator p is simply the variable p times identity, and therefore the differentiation d by dp makes sense. If I go back here, I could well argue that this is the same as I h cross d by dpx of px to the n. And if I look at this commutator, this is the same as minus I h cross d by dx of x to the power of n. Once again, analogous to what I did in the case of the momentum operator, here I have removed the hat from x. That's because in a function space, which is the coordinate space, I could talk about the operator x as simply the real variable x times identity, and in this case the differentiation, as I have put it here, makes sense. I will discuss these spaces in a later lecture. From all this, it strikes me that I might be able to make this very important identification, that if I have to write x in terms of p, the identification would be that x can be written as plus I h cross d by dpx, and px can be written as minus I h cross d by dx. In other words, I can give a differential operator representation for the position operator and the momentum operator. I have already told you that this in matrices would be infinite dimensional matrices, and here are differential operator representations. Clearly they will have to act on functions. It automatically tells us that in an example like this, we are dealing first of all with an infinite dimensional linear vector space. Not only that, we are dealing with a space where there are differential operators, and therefore when they act on states, the states should be in a function space. This brings us to a point where we need to understand linear vector spaces, which are actually function spaces, functions of some real variable x, and those are the states, and the operators could be differential operators which act on those functions. The differential operator clearly acts linearly, because if I have d by dx acting on some function psi of x plus some other function phi of x, it simply does the following. It gives me d psi of x by dx plus d phi of x by dx, and so on. It is equally clear that the action of x d by dx on a function psi of x is not at all the same as the action of d by dx x on psi of x, because this is simply x d psi by dx, whereas that gives me a psi of x plus x d psi by dx. So these do not commute with each other in terms of operations. X d by dx does not work the same way as d by dx of x. But before we go on to understanding function spaces, in particular we would be interested in the space of all square integrable functions, which I did mention in one of my earlier lectures. The space is L2, which is the space of all square integrable functions, and there is a range a to b, could be minus infinity to infinity, and these functions satisfy is finite. And x is a real variable. A space like this is an infinite dimensional space. It is an infinite dimensional linear vector space on which an inner product structure is defined. Just to recall, the inner product in general of psi with phi is the same as phi psi star. Sometimes you use the notation psi comma phi. I have used the Dirac notation. So this is the same as phi psi star. The inner product is in general a complex number. Further, the following properties hold for an inner product. The inner product of psi with a phi plus b chi, where phi and chi and psi are states, is a psi phi plus b psi chi. In fact, we have used this all the time when we discuss 2-level atoms and 3-level atoms. Of course, the inner product of psi with a state a phi, where a is a scalar constant, is simply a psi phi. Of course, it follows that a psi with phi is a star psi phi, and the inner product of psi with itself is greater than or equal to 0, 0 only if psi is the null vector. So these are the properties that we did come across in our discussion earlier, but I have merely listed them out here for convenience. We will be dealing with infinite dimensional spaces where the inner product structure is defined, and we would also need the concept of a norm or the length of a vector. So norm psi is the positive square root of psi with itself. This is simply an extrapolation of what we already know. Suppose I have a vector a ex plus b ey in 2 dimensions, where ex and ey are unit vectors, then v dot v is simply a squared plus b squared, and this is the analog of psi psi, and therefore the length of v is the positive square root of a squared plus b squared, and that is the analog of the norm. So we have this inner product structure, and we are dealing with an infinite dimensional function space in the context of the commutator of x with px. But before we proceed, given this particular identification, that in terms of px, x can be written as a differential operator plus ih cross d by dpx, and px is minus ih cross d by dx, it is clear that a straightforward extension tells me that the momentum operator p would be simply minus ih cross del, where del is d by dx unit vector ex plus d by dy unit vector ey plus d by dz unit vector ez, and this is in 3 dimensions. Given this identification, without worrying too much about the Hilbert space structure or the linear vector space structure right now, I want to illustrate a very important property. Consider 3-dimensional space where I have the Cartesian axes x, y, and z, And suppose I rotated about the z axis by an angle theta, rotated taking x to x prime and y to y prime. We know that x prime is x cos theta plus y sin theta, and y prime is minus x sin theta plus y cos theta, and z prime is the same as z. What happens to a function of x, y, and z? So I consider psi of x, y, z. Obviously, it goes to a function psi prime, which is a function of x prime, y prime, and z prime, but z prime is the same as z. Now, psi prime of x prime, y prime, z prime is the same as psi prime of x cos theta plus y sin theta minus x sin theta plus y cos theta z. For theta small, so that I can just retain the first order in theta in a Taylor expansion. For theta sufficiently small, so that I can ignore order theta squared and so on. This is the same as psi prime of x plus y theta minus x theta plus y and z. I could make a Taylor series expansion, and that is just going to be psi prime of x, y, z plus delta psi prime by delta x times y theta minus delta psi prime by delta y times x theta plus order theta squared terms and higher order terms, which I ignore. Well, I can write this as 1 plus theta times let us say 1 minus theta times x delta by delta y minus y delta by delta x psi prime of x, y, z. If I retain the next term, the term that is proportional to theta squared, I will find that I am going to get the next term in the exponential series here. You consider this term, delta by delta y, in terms of what is written here is simply IPY by h cross. Similarly, delta by delta z is IPZ by h cross, and therefore I have psi prime of x prime, y prime, z is 1 minus I theta by h cross xpy minus ypx plus, if I worked out the next order, I would get this. A word of caution, as I stated earlier, one should remember that xpy minus ypx the whole squared, when expanded, I should retain the order of operators properly, but this just acts on psi prime of x, y, z, telling me that psi prime of x prime, y prime, z is exponential of minus I theta by h cross Lz psi prime of x, y, z. This is a very important result. First of all, this should strike a bell. It should remind you of the manner in which the spin matrices behaved This theta is like the group parameter. Lz is the generator of the transformation about the z axis. In this case, orbital angular momentum is the generator of space rotations. Simply in analogy with what I had said earlier about the spin matrices, Lx, Ly and Lz are the generators of an SU2 transformation, but this time in physical space, and the commutator Lx, Ly is IH cross Lz cyclic. These are operators, you could put the hat there. I could introduce L plus and L minus as before, and I have a vector L which is Lx Ex plus Ly Ey plus Lz Ez, which behaves under this transformation in the same manner in which the coordinates x, y and z behave. So here is another example of the SU2 group. So spin is simply like orbital angular momentum, except that it is in an internal space and this is in physical space. And I have just demonstrated to you that once this identification of P, the vector P or the operator P as minus IH cross operator del, once that identification is complete, it's pretty clear from what I have done that angular momentum is the generator of space rotations, and this is the angular momentum algebra. So we've really handled two examples of the SU2 algebra. One is the orbital angular momentum algebra and the other is spin. But orbital angular momentum would be in an infinite dimensional linear vector space. I will stop here, and in my next lecture I will talk about simultaneous measurements, what happens to expectation values under simultaneous measurements of objects which do not commute with each other, operators which do not commute with each other.